Starting on page 1 of the review, and the first problem that I would like to look at is numero 2. So on number 2, what type of equation do we have? Exponential. And I want you to add a couple of things to the instructions here. I want you to add that you need to graph the asymptote. And state the transformations. States transformations. Why do we need to state the transformations? What do those do for us? They help us figure out where the asymptote is located. So let's go ahead and start with number 2. The 4 does what? V-stretch. By 4. The 1/5 is the base. Doesn't do anything except tell us that this is a decay function. What about that plus 3 up with the x? Left 3, very good. And then the minus 1? Down 1. So if this is an exponential graph, and I would probably go ahead and write this down. Exponential graphs always have a horizontal asymptote and a domain of all real numbers. Whereas log functions have what type of asymptote? A vertical one. And remember, our dumb little way of remembering that is make that vertical asymptote into a little tree. And then if it helps you remember, you can draw the little lion. And that lion is saying, "Roarn," for a range of all real numbers. So exponential functions have a horizontal asymptote and a domain of all real numbers, whereas log functions have a vertical asymptote and a range of all real numbers. Now you can read those directly from the graph, but having that asymptote knowledge is helpful, especially when we go to figure out where that asymptote is based on the transformations. So where does our horizontal asymptote start for this one since it's exponential? So normally it's at 0, but if we apply those transformations, vertical stretch, nothing. Left 3, same vertical line. Down 1, bloop, it slips down 1 unit. So we're going to go ahead and draw it going through -1. So that's part of this graphing, is being able to draw in the asymptote. Now we are going to pick our points. Now the goal with this is we want to choose points that are fairly friendly on our calculator to find. So let's go ahead and try to get our exponent to be equal to what easy values? -1, 0, and 1. Perfect. So I want that whole thing, the x plus 3, to be equal to -1, 0, and 1. So we want to ask ourselves, what x values can I plug in to get those power values? What can I plug in for x so that the exponent is equal to -1? -4. And then -3 will give us 0. And then -2 will give us 1. Now from here, you could type those values in on your calculator to evaluate. Be careful that you're not forgetting the -1. Sometimes that's a common error, is losing stuff to the right of the exponent. So I'm going to go ahead and try to do this one by hand, and we'll just see what happens. So -4 in for the x plus 3 is -1. What's 1/5 to the -1? 5. Then 5 times 4 is 20, and 20 minus 1 is 19. Well, that's just a super fun point to have to graph. We're not going to graph it because it's off the graph, but just to keep in mind that our graph will be going way up here at -4, 19. -3. What's 1/5 to the 0? 1. 4 times 1 is 4. 4 minus 1 is 3. So -3, 3. That's our next point. Thank you. So -3 of 3. And then our last point, -2. 1/5 to the first is 1/5. 4 times a fifth is 4/5, and 4/5 minus 1 is a -5. Or if you used your calculator, you can say -0.2. I don't care which one you use, just so long as you can plot the point. So we've got -2 and then down a fifth. So it looks like we are heading for the asymptote on the right side. Leveling off. Again, this is a decay function, so think Red Bull crashing. And then it goes exponentially up towards that one point, the -419, which we aren't going to graph. So what's our domain? All real numbers, or -infinity to infinity. Pick your poison on that. And then what about our range? First, what variable do we use for range? Y. And are we covered above or below the asymptote? Above, so greater than what? -1. Perfect. So that comes from that asymptote. So these are the things I'm going to be looking for. The asymptote, the graph with arrows on both ends of it, your table work, and then the domain and the range. Anybody have any questions on graphing the exponentials? Can I check myself on my calculator with this? Yeah, is that a good idea? Yeah, so if you wanted to plug that into the y equals and look at the graph, not a bad idea, but I'm going to be looking for this work. So, folks, let's go ahead and let's go down to number 6. What type of equation is this one? It's a log equation. Let's start by stating our transformations just like we did above. What's that negative doing? Vertical reflect. The 2, it's the base. Doesn't do anything, just like before. And the -3 on the inside. Right 3. So we've got a vertical asymptote. Where's that vertical log asymptote start? It starts at 0. If I reflect it and flip it upside down, does it move? No. If I move it right 3, does it move? Yes. Yes. So our vertical asymptote is going to be going through 1, 2, 3. So what do we do to get our table points for this? What do we normally do when we have a log? Can't log a log. Put it in exponential form, but we have a slight snag. So I'm going to go ahead and show this work down below. So y equals negative log base 2 of x minus 3. Because when I start doing my big animal ears with this, the 2 is my big, the base. The stuff inside the log is the animal. Y is the ears. So what's the awkward thing that's not a part of any of it? The negative. So how can I move the negative so that it's part of something? What are we going to do to move it over to the other side? We're going to divide by -1. So goodbye. And then I get negative y equals log base 2 of x minus 3. Ooh, let's zoom in some. Now we can put this in exponential form. So big animal ears. So the base is 2. The animal is x minus 3, the answer. And the exponent is negative y. What's our final step with this? Yep, isolate the x. We want it to be an x equals equation because that just makes it easier to use when we're plugging in our points. So there it is. There is our log written in exponential form. It is still a logarithmic equation if you're like, yeah, but the variable's in the exponent. It's the output variable that's in the exponent, which means this is still a logarithmic equation. So we're going to go ahead and make our pretty little table. And we're going to use 2 to the negative y plus 3 equals x. So now, similar to what we did with exponentials, instead of trying to get our x to be equal to -1, 0, and 1, we're going to try to get this exponent with y to be equal to those power values of -1, 0, and 1. So -1, 0, and 1, but we're plugging in y values to get the x values. So what can I plug in for y to give me that power value of negative 1? 1. We plug in 1, we take the opposite of it, boom, negative 1. What can I plug in for y so that I get 0 up in that exponent? 0. Opposite of 0 is 0. And what about to get positive 1? Negative 1. So that's what I'm plugging in. That's what I'm getting for those powers. So let's see what happens when we plug these in. What's 2 to the negative 1? 1/2. And then plus 3? 3.5. We plug in 0. Negative 0 is 0. 2 to the 0 is 1. And 1 plus 3 is 4. Then negative 1. 2 to the negative 1 is 2 to the positive 1. 2 to the positive 1 is 2. 2 plus 3 is 5. Not bad at all. So now we're going to plot these points. This x with that y, that x with that y. So just be careful that you don't accidentally use those yellow values. Those are the power values. They're what we want the exponent to look like, but they're not actually what we're plugging in for x and y. So 3.5, 1. So forward 3.5, up 1. Boop. 4, 0. Boop. 5, negative 1. Bonk. So then it looks like we are leveling off towards the asymptote going up this way. Making sure you put an arrow on that side, and then we start swooshing exponentially down and out. See if you can state the domain and range for this one. What's the domain? X greater than 3, which is because of the vertical asymptote. What about the range? What y values are going to get covered? All of them. Roar. Hooray. Folks, any questions on the graphing? So logs put in exponential form, isolated to get all your big animal ear stuff lined up, and then using those power values to get your table. Turn the page. Folks, with writing in exponential form, we're literally just rewriting. Remember, logs go in the order of the elephant holding the log, big animal ears, base answer exponent, whereas exponential form is base raised to the exponent equals the answer. So in these first two sections, you are just rewriting, going back and forth between the two forms. On 11 through 15, we are evaluating. Folks, how do we evaluate one log? You do the big animal ears. You put it in exponential form. So one log, exponential form. Doesn't matter if you are solving or evaluating, that rule stays intact throughout this whole unit. So if you find it helpful, if I was going along doing number 13, big animal, what am I going to put for my ears? Equals x. So we're trying to find what the exponent is on this problem. So if you want, and I will prompt you to do this on the test tomorrow, you can put in those equals x. So let's go ahead and work number 13. Big, base 3. Animal, answer is 1/9, the exponent that goes with the 3. So how do I make that 3 look like 9 in the downstairs? Take it to the negative. 2. And if you're like, that doesn't vibe, Ms. Caro, we can do the same strategy that we were doing earlier with putting equations or solving exponential equations. We want to try to get the same base. So can I rewrite 9 as base 3? 9 would be 3 squared, so 1 over 9 would be 3 to the negative 2. And that shows me x equals negative 2. I'm going to give you a hint on number 14. First, what's my big on this problem? 10. When there's no base explicitly written, boom, it is base 10. So big, animal, ears, base 10, exponent is x, answer is 0.01. On your calculator, 0.01, math, enter, enter, is 1 over 100. So with the decimal, it's like, oh my gosh, I guess we'll just log both sides, which you could do. But if I write it as 1 over 100, can I write 1 over 100 as base 10? Yeah. What would it be? 10 to the? Squared. -2. To the negative 2. So x is negative 2. Next one's a little bit weird as well. We've got a natural log. What's natural log the same as? Log base e. So I replace it first, and then e is also in the answer part, and this is equal to x. So big base e, animal is e, and ears is x. Lots of letters here. E to the x equals e. What's x then? 1. Questions? All right, next, expanding and condensing. For expand, everything on the land. Expand everything on the land. What does that mean? What don't we want when we are expanding? We don't want exponents. We want to have as many coefficients as possible. So everything on the land means bring all of those powers out in front as coefficients. Condensing, we want to get it down to 1 log, and here we send our coefficients to the clouds or back up as exponents. So condense, coefficients to the clouds, expand, everything on the land. So let's go through and write what we are trying to do on each problem. Anytime we have 1 log, we're going to try to expand it into multiple logs. So is 16 expand? Yeah. So 16 is E. 17 has 1 log, so that's E. 18 has 2 logs, so we'll condense that one. 19 has a whole mess of stuff. That's going to be condensing too. So 19 condense as well. 20 will expand. 21 condense. 22 condense. 23 expand, 24 expand, 25 condense, 26 expand, and 27 condense. And we're going to go through a few of these together. So how's about number 16 first? So we've got log base 2 of x to the 3rd, y raised to the 3rd. There's a few different options for how you can start this problem. I personally like to approach this from a PEMDAS standpoint. and handle distributing that exponent in first. So I'm going to power up and distribute that 3 to the x cubed and to the y. So that will give me log base 2 of x to the 9th y cubed. Now we want to expand it. So expand everything on the land. First, we've got multiplication in the answer part. What operation do I use to expand? Addition. So log base 2 of x to the 9th plus log base 2 of y to the 3rd. So expanding, we're getting separate logs. Our final step is everything on the land. We're going to take those powers and move them out in front as coefficients. So expand everything on the land. So 9 log base 2 of x plus 3 log base 2 of y. So expand everything on the land. So let's do number 23 together next. Because 23 is kind of a tricky one. So on 23, this stuff is inside the log. There's nothing to simplify at this point. Now, as far as how I'm going to expand it, I've got 2 operations going on. I've got multiplication in between those, and I have division, and I got multiplication in between the 2 and the y. So when we start expanding, I'm going to have common log 9 plus common log x to the 4th. So the multiplication turns into addition. I'm dividing by the 2, so minus log 2. Now, these two are joined by multiplication, but I am dividing by both of them. So since the y needs to go to the downstairs as well, am I going to have a plus or a minus in front of log y? A minus. And I would say that's one of the tougher things to remember. Division is minus, and whatever is in the denominator is going to have a minus in front of the log. Expand everything on the land. Final step would be moving that 4 out in front as a coefficient. So common log 9 plus 4 log x minus log 2 minus log y. Let's do a condensing one. How about number 22 right next to it? Before I can condense, can I just mush those 2 logs together into 1 log? Right now?
No.
Why not? Gotta move the 2. Gotta send that coefficient to the clouds first. You can't condense logs that don't have the same front end. So we have to move that 2 back up as an exponent. So send that coefficient to the clouds. So then we have log base 5 of m minus log base 5 of n squared. So now we're trying to put the logs together, condense it into 1 log. These 2 logs are separated by subtraction. So what operation will we use to condense? Division. So log base 5 of m on the top, n squared on the bottom. Final answer. Questions on any of those ones? Let's go ahead and look at number 19. 19 is kind of gross. So on 19, it's kind of tough to tell what's going on here with these parentheses, but that 4 is on the outside of those parentheses. So from a PEMDAS standpoint, what I would do is distribute that 4 to everybody. So 4 natural log x plus 8 natural log y. minus 4 natural log z. So I got 3 logs. I want to condense it into 1 log. What are we going to do with those coefficients? Send them to the clouds. Put them back up as exponents. And remember, you don't take the sign with it. We leave that negative there to show that that will be condensed using division. So natural log of x to the 4th, natural log of y to the 8th, natural log z to the 4th. So these logs are separated by addition, so we'll condense using multiplication. This one is separated by subtraction, so we'll condense using division. So natural log of x to the 4th, y to the 8th on the top, z4 on the bottom. If you want to enclose it in parentheses, you certainly can. And there's condensing. Turn the page. The solving. This is the stuff that we did the homework quiz on today. So if that did not go well, you may want to do corrections to that or try reworking it as part of your review. We have 2 types of equations that we can encounter. The first is exponential. When I have exponential equations or variables in the exponent, we want to try to get the same bases. But if we can't, what do? Log both sides. The other type of equation we have is the logs. Now, if we have 1 log, we put it in exponential form using big animal ears. 2 logs, you might condense or you might cancel. It depends on if those 2 logs are on the same side or on different sides. So condense, we'll write same side. Cancel, different side. If we have 3 logs, you'll condense first, and then you'll either have 1 log or 2 logs. What's the other thing we got to remember with logs? Extraneous solutions. The answer part of the log has to be greater than 0. So, folks, I want you to see if you can do number 31. I'll put that little half sheet up there if I can find it. So try number 31. Folks, can we rewrite these as the same base? I'm looking at that 1/5 first. Can I rewrite 1/5 as a smaller base? Yes, 5 to the negative 1. So that gives me a clue that I probably want to write 625 or 1 over 625 as base 5 as well. So I'm going to go to base 5. Squared, cubed, ding, 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 ding. 4th is 625. So a 5 to the 4th is 625. 5 to the negative 4th is how I get 1 over 625. See if you can solve it from here. you should be getting x equals -4. How did we do? A-okay. All right. So, which other ones do I want to do? Let's go ahead and go down to number 41. So 41 and 45 both have base E involved. So first, is this an exponential equation or a log equation? It's exponential. So there's an exponential, there's a variable in the exponent, so this one would be exponential. Now, can we get the same bases? It's like, well, first of all, there's a lot of bases and a lot of numbers going on here. Let's first isolate our base, which is the one that has the variable. So we're going to isolate e to the x, adding 24 equals 40. Divide by 5. Got to divide by that 5. Because now we just have base E compared to base 8. Can I rewrite those as the same base? Nope. E's a weird little number. Can't do it. Now, normally we log both sides, but with E, I want you to put a note up here. If base E, we natural log both sides. So base E, natural log both. And it's like, all right, well, natural log, smatral log. Like, why does it matter? What does natural log do for us that regular log can't? Natural log cancels out that E completely, which means the X gets to come right down out in front. And I just have X equals natural log of 8. So instead of having common log 8 divided by common log E, now I just have natural log of 8, which I can type in on my calculator. So natural log of 8, that's that ln button next to your 4. And if I told you to round this to 3 decimal places, 1, 2, 3, we check the 4th digit to see if it bumps us up. That's a no, so 2.079. No need to check for extraneous solutions because that was not a logarithmic equation. It was an exponential equation. If you're like, but there were logs in there. Yeah, as part of the work, but not in the original problem. Folks, I want you to, with that in mind, try number 45. We see we have an exponential. We see we have E. We're going to isolate our bases. So subtract 7. 6e to the 4x equals -3. Divide by 6. And e to the 4x is a -1/2. Can I make -1/2 look like base E? Nope. So we natural log both sides. Goodbye, natural log of E. And the 4x comes out in front. Now there's something interesting that happens over here. Folks, can I have that negative 1/2 inside the log? What's that going to give me when I type it in on my calculator? Error, because negative 1/2 is not greater than 0. So what does that tell me about this as far as what x is going to be equal to? No solution. Let's go ahead and try 42. Our plan of attack. We have one log. Put it in exponential form. Big. Animal. Ears. So 3 to the negative 2 equals x squared. Can I solve this for x? How do I get rid of the squared with the x? Square root. If you're like, whoa, what? What about that? Well, this is actually the square root of 1/9. So x is plus or minus the square root of 1/9. Can I simplify that? You may remember from the last unit, take the square root of a fraction, we square root the top, we square root the bottom, and ta-da! We get plus or minus 1/3. Now the question is, do both of those work in the answer part of the log? Positive 1/3 squared gives us 1/9. Negative 1/3 squared also gives us 1/9. Do those both work in the answer part of the log? They do. Plus or minus 1/3 is indeed our solution. Taking it to number 44. This one's a little bit gross because we got a whole mess of logs going on. All those logs that are on the left side, we're going to condense them together. So log base 7 of 64 over 8/3, and then times 2 equals log base 7 of 4x. So I'm only dividing by the 8/3. The 2 gets multiplied. How do we divide by fractions again? Keep, change, flip. So this would be 64 times 3 over 8 times 2. We do some super fun canceling, and we get an 8 on the top. 8 times 3 is 24, times 2 is 48. So log base 7 of 48 equals log base 7 of 4x. Phew. From here, cross off the logs. 48 equals 4x. And x equals 12. Plugging into the answer parts of the log, of all the logs, 64 is greater than 0. 8/3 is greater than 0. 2 is greater than 0. 4 times 12 is 48. That's greater than 0. So x equals 12 is our solution. Questions? Turn the page. Last problem we're going to go over is number... Actually, there's 2 things we need to go over.
So you have 2 minutes.
We got it. First, on number 48. Number 48, generally accepted new card, yada, yada. Change 2020 to 2015. So number 48, change it to 2015. On number 46, cells grow at a rate of 9.3% every hour. If our unit in the problem is hours, what am I going to use for T for 1 day? 24. So make sure you're being careful with your units. You're being careful with years since a particular time. That's the only thing that really, I think, makes 8.4 challenging. So as you're working through those problems, use your note formulas, because I will be giving you those 3 formulas for the test tomorrow.
Wait, so we don't need another formula?
Don't have to have them memorized, just how to use them.